In this lesson, you will learn about the architecture of FortiOS. After completing this lesson, you should have the practical skills and knowledge required to describe how FortiOS processes a packet, describe how FortiOS uses memory, diagnose high memory and high CPU problems, differentiate between system, kernel, and FDS conserve modes, and optimize the memory usage. In this section, you will learn about the life of a packet. Parallel Path Processing, PPP, uses the firewall policy configuration to choose from a group of parallel options to determine the optimal path for processing a packet. That path that PPP chooses also depends on the hardware configuration. This slide shows all the steps that a packet goes through as it enters, passes through, and exits a FortiGate without any hardware processors. Now you will learn about how FortiGate uses memory. To understand how the FortiGate uses its memory, you need to understand the architecture of FortiOS. The heart of FortiOS is its kernel. The kernel is where FortiGate makes some of the most basic and important decisions, such as how to route a packet, or when to offload a session to an MPU processor. FortiOS runs over hardware. The device drivers bridge the kernel with the hardware. The user space is located above the kernel. Several application processes, or daemons, run in the user space. Above the kernel and the user space is the configuration layer, which is basically composed of two modules, the command line interface and the graphical user interface. How FortiGate's memory is segmented depends on the model. There are two cases. One case applies to 32-bit models with more than 1 GB of memory. The second case applies to both 64-bit models and 32-bit models with less than 1 GB of memory. Let's take a look at the first type of model. When FortiOS is 32 bits and the system memory is more than 1 GB, the kernel cannot access the whole memory space directly. So memory paging is used to reach the portion of the memory that cannot be accessed directly. The part of the memory that the kernel can access directly is called low memory. The part of the memory that is accessed using memory paging is called high memory. The command diagnose hardware sysinfo memory displays the following: the total amount of low memory, the amount of free low memory, the total amount of high memory, the amount of free high memory, the total amount of system memory, and the total amount of free memory. For models running 32-bit FortiOS with less than 1 GB, and for models running 64-bit FortiOS, the kernel doesn't need to use memory paging to access the whole memory space. In those cases, the command diagnose hardware sysinfo memory shows a size of 0 kilobytes for the total high memory and free high memory. All the memory space is considered low memory. FortiGate allocates memory for 5 main purposes: kernel memory slabs, system I/O cache, buffers, shared memory, and process memory. You will learn about each of these purposes in this lesson. The kernel memory slabs are collections of objects with a common purpose. They are used by the kernel to store information in the low memory. The slide shows an example of some slabs. There are slabs for storing information about TCP sessions. The entries in the route cache are also stored in low memory slabs. To check how much memory is being allocated to kernel slabs, use the command diagnose hardware sysinfo slab. The first column shows the slab name. The second column shows the total amount of active objects, then the amount of available objects, and the size of each object. The total amount of memory allocated to each slab type can be calculated by multiplying the number of available objects by their size. You can use the output of this command to determine how much memory the session table is using. If that value is too high, it might indicate that the configuration needs some tuning, for example, setting shorter session time to lives, or that the FortiGate model is too small for the amount of traffic crossing the device. The system I/O cache is used to speed up the access to information stored in the hard and flash disk memories. Some processes, such as logging, WAN optimization, and explicit proxy, store information in the hard disk, so they get the performance boost provided by this memory allocation. An I/O cache page is labeled as active when it has been recently accessed. It goes to inactive state after not being used for some time. An inactive page can be reclaimed by the kernel if needed. The command diagnose hardware sysinfo memory displays the total amount of memory allocated for I/O cache. It also lists the amount of memory allocated for buffers. Above the kernel layer, there are multiple application processes, or daemons, running. The operating system allocates separated blocks of memory for each process. One process can access the memory that was allocated to it, but it cannot access any memory that was allocated to a different process. So, a process cannot share information with another process by reading or writing data into the memory allocated to that other process. For that purpose, the operating system dynamically allocates shared memory, SHM. The SHM can be accessed by multiple processes, allowing the sharing of information among them. You can see how much memory space is being used by each process. The command diagnose sys top shows that information in the last column. The command also displays, for each process, its ID number, its state, and the amount of CPU usage. You can specify the refresh frequency and the number of lines to display. While the command is running, you can press Shift-P to sort the processes by CPU usage, or Shift-M to sort them by memory usage. To stop the command, press Control-C. Another useful command for displaying information about process memory usage is diagnose sys top summary. The -H option displays the different options available for this command. You can use the option -S mem to sort the processes by memory usage, the option -I60 to refresh it every 60 seconds, and the option -N10 to display the top 10 processes. One advantage of this command is that it shows the total amount of memory allocated by all forked and child processes, including shared memory. In the case of diagnose sys top, each child process is displayed separately. Here, we have an aggregated view of all of them. The output also shows the amount of file descriptors allocated. If the amount of any of the descriptors keeps constantly increasing, it might indicate that there is a memory leak problem. If a process has forked, the number of child processes is displayed after its name. This table shows some of the most common processes. This table shows more of the most common processes. The command diagnose sys top shows the state of each process. A process can be in one of four states: sleeping, S, running, R, do not disturb, D, or zombie, Z. The S and R states are normal. It is also normal if a process goes briefly to D state. The Z state is not normal. Also, it is not normal if a process stays in D state for a long time. This usually indicates that the process is not working properly. Now that you have a better understanding of how FortiGate uses memory, let's look at conserve mode. If your FortiGate memory usage is high, you should examine the event log. Look for messages related to conserve mode. Memory conserve mode occurs when FortiGate doesn't have enough RAM available to handle traffic. Content inspection, especially proxy-based, increases memory usage beyond simple firewall policies. In other words, when antivirus is enabled, FortiGate is more likely to use more memory, which can cause FortiGate to go into conserve mode. You can determine whether antivirus or any other process is using too much memory by running the CLI command diagnose sys top. There are two types of memory conserve mode: kernel and system. Two margins or thresholds determine when FortiGate enters and exits the kernel conserve mode. For all FortiGate models that have 64-bit CPUs, the margins for kernel conserve mode depend on the total overall memory. When a FortiGate is in kernel conserve mode, any proxy inspection is bypassed, and administrators cannot perform configuration changes. Like kernel conserve mode, two different thresholds determine when FortiGate enters and exits system conserve mode. The margins also depend on the total amount of overall memory. This slide shows the entries that are generated in the event logs when a FortiGate enters kernel and system conserve modes. AV fail open is the CLI setting that controls FortiGate's behavior while it is in system conserve mode. File descriptors, FDs, are used as handlers to access input and output resources, such as a file. FortiGate will become unresponsive if all available FDs are used. To prevent this from happening, a new conserve mode was introduced in 5.4. FDS conserve mode will prevent a single process or process group from using up all available free FDS. This allows the system to continue to operate under heavy load. A FortiGate enters in FDS conserve mode when the amount of free available FDS is less than 5%. FDS conserve mode only affects the WAD processes. This command is used to determine if a FortiGate device is currently in system conserve mode, FDS conserve mode, or both. An option related to fail open is AV fail open session. This setting is used when a proxy on the FortiGate runs out of available sessions to process the traffic, not during a high memory situation. If you enable AV failopen session, then FortiGate acts according to the AV failopen setting. Otherwise, by default, it blocks new sessions until proxy connections become available. FortiGate has one more mechanism to free memory when there is not much available. If the kernel cannot allocate more memory pages, it deletes the oldest sessions. The command diagnose sys session stat shows the number of sessions deleted by the kernel due to this mechanism. FortiGate has a mechanism to protect memory usage against some forms of DOS attacks. FortiGate categorizes an entry in the session table as an ephemeral session when it is a TCP session that is not fully established. In other words, a three-way handshake is not completed. Or it is a UDP session with only one packet received. During some DOS attacks, the number of these types of sessions tend to increase abnormally, potentially consuming the unit memory. FortiGate sets a hard limit in the maximum number of ephemeral sessions that can simultaneously exist in the session table. What can you do if a FortiGate enters in conserve mode frequently, or if its memory utilization is too high? You can optimize memory usage by fine-tuning the FortiGate configuration. Many FortiGate processes, such as DLP and AV scanning, are memory intensive. So memory optimization is important, especially in small units, to guarantee that these processes will stay away from memory conserve mode. This slide shows some recommendations for optimizing memory usage. These tips might significantly increase the available memory in the device that is frequently going to conserve mode. The first and most logical step is to disable features that are not required. For example, if the network already has a FortiMail doing anti-spam, an administrator does not need to do anti-spam in FortiGate. Also, usually not all the IPS signatures are required. Another recommendation is to reduce the maximum file size to inspect, which is set to 10 megabytes by default. This value can be reduced to 2 or 3 megabytes without significantly reducing the virus caching rate. Additionally, you can reduce the amount of memory allocated to some caches, such as the ones for FortiGuard and DNS. The FortiGate session table can consume an important portion of memory, especially in networks with a high rate of traffic. By default, a session without traffic remains in the table for up to 1 hour. Although this high a time to live, TTL, might be required by some applications, in most networks you can reduce the session TTL. When you reduce the TTL, FortiGate ages out idle sessions much quicker, increasing the amount of available memory. There are 4 places in FortiGate configuration where the session TTL can be reduced. 2 of them are globally for all the traffic and on an IP protocol and port number basis. The other 2 places where the session TTL can be reduced are for each firewall policy and for each application control. If an application requires a high session TTL, you can reduce the TTL globally to 5 minutes. However, set it to 1 hour only for the specific application port number or firewall policy. Most TCP session timers can also be reduced from their default values without causing problems to applications. This slide shows some recommended values that are equal to or below the default values. Use these recommended values to optimize the memory usage. The TCP half-open timer controls for how long, after a SYN packet, a session without SYN ACK remains in the table. The TCP half-closed timer controls for how long, after a FIN packet, a session without FIN ACK remains in the table. The TCP time wait timer controls for how long, after a FIN ACK packet, a session remains in the table. A closed session remains in the session table for a few seconds more to allow any out-of-sequence packet. In this lesson, you learned about the following: the life of a packet, how FortiOS uses memory, the most common FortiOS processes and process states, system and kernel conserve mode, FDS conserve mode, and optimizing memory usage.